Hello again, I'm Dmitry Kulik. This is the third part of a short tutorial about new functionality in CemGEMS release 0.7.0. In this part, we will consider how the cement hydration processes can be treated after the introduction of the process setup table, the new feature. So we start then with another new recipe made of cement 2 type template with mineral composition of cement clinker and supplementary cementitious materials, as you see here, and with the new process of the type hydration with modified Parrot-Killoh model run in logarithmic time scale. So we click on simulate process as usual and wait until something happens. So now we have the recipe calculated, the partial equilibration, so you can see now it's pretty rich composition both at the beginning, because it consists of clinker and supplementary cementitious materials, gypsum and fly ash. And also there is quite a lot of various hydrated phases forming, along with some residual fly ash and some residual clinker. This calculation is by default done for 28 hours reaction time. Now we would like to simulate what happens during the cement hydration, so to say, from the beginning. And this is done using this process called hydration mP&K, logarithmic time. We can see that it's a typical picture, so clinker phases dissolve slowly. Also, fly ash dissolves to some relatively small extent, and the hydrated phases form. Mainly what forms is calcium silicate hydrate, some portlandite, and some siliceous hydrogarnet, then adringite, monocarbonate, a little bit calcite. So this is a typical behavior for this kind of blended cement. Now, using the process settings table, we can watch really how this simulation is set up in detail. So we just go to this process setting table widget, expand it by clicking on triangles, and we can see now that this table consists of two subtables. One is called spans. We have considered this sort of process settings in detail in the previous part, and another is called Params. I will come back to Params later. I would like to stress that in this case, when we simulate hydration, we need to set up a time scale. So in this case, time scale is set in hours, logarithmic stepping, from -1 to 4, which means that we start from 10 to -1 hour, 6 minutes, and then go incrementally up to 10,000 hours in 101 steps. So this time scale controls then everything else in this process simulation. In particular, it controls this spans, params, and each of the param entries applies through its target path to certain clinker phase, in this case A light, B light, aluminate, ferrite, and also to some constituents of supplementary cementitious material, slag, calcined clay, or fly ash. In this particular example, or in this template, both recipe and process, we actually have only active the fly ash, because the other two supplementary cementitious materials are set to 0 quantity in the recipe. But this can, of course, be changed, and as long as the quantity is not 0, the respective param entry with the target will be activated too. So there are two built-in models, and one of them is modified Parrot-Killoh. So it's implemented internally in CemGEMS backend. But what we have externally is the parameter values of this modified Parrot-Killoh model, which is described along with the parameters in this paper here. And now the parameters are listed in any order, but with strict parameter names. That means the program will only accept such names, regardless of order, and then, of course, the parameter value. This is the comment field, and it's good for changes. If you change some parameter, you can indicate here, for instance, which value it used to have, or why you have done this change. So, and well, then, as I said, it runs internally. So if we take a look at what it produces, so we see that the target is always react extent or degree of reaction of the respective constituent or of cement or SCM material. If we have a look at reaction extents here, we can see 4 curves that are produced by modified Parrot-Killoh model. Why not 5? Because in this particular recipe the initial amount of magnesium oxide is 0, so it's not activated. The other 4 work. And also there is this one curve for fly ash, reactive fly ash, which is a constituent in SCM material. So you can see how these models reproduce the change of reaction extents in time. Now we come back to the list of parameters, and then we can take a look at another type of the model, which is a 5-parameter logistic equation. Typically, this kind of model is used for supplementary cementitious materials, and in some cases also for clinker materials or clinker components, constituents, especially in calcium sulfoaluminate cements, where the Parrot-Killoh model is not actually applicable. In this case, the parameters are also named and can follow in any order, but strictly with those names, A, B, C, D, G. And in the documentation, you can find a description of this logistic equation and the meaning of those parameters. So actually, the first 2 entries in this section for slag and calcined clay are not active because these constituents of SCM are given as 0 amounts. I can show you here in the recipe. So if we expand the input recipe and then SCMs, you can see that we only have limestone and we have fly ash, reactive fly ash, and that's it. And other things like slag or calcined clay, they are given in 0 amounts. For that reason, their respective hydration kinetic equations are not activated. So now we come back to, so we actually have only this last one really up and running. The target paths, they work in the same way as for temperature that we considered in the previous part of the tutorial. So basically you need 2 double clicks. For example, if I now remove this, say, target path for calcined clay and put here something like test, of course it will not work as it should, because the program will not find what to change. But now if I double click here on this field, it will change the color, and this is an indication that now I should go to initial recipe, SCM, find this calcined clay, and click on the field that this param entry in the process definition should change. And this is the reaction extent. So I do double click here, the colors disappear. Then I go back to my process and see that the target path is safely restored, which is of course very convenient because otherwise it would be necessary to count these indices and all things by the user himself or herself. In exactly the same way as with the spans table, you can use the JSON editor here, which now shows both input params and input spans arrays. Any entry in this arrays can be duplicated using this menu or removed. And in this way you can reconfigure the process setup document. Now, just to give you some feeling how this manipulation with parameters of hydration kinetic equations can affect your calculations, let us do a small exercise. So we actually would like to know what's going to happen if the fly ash, the supplementary cementitious materials, reacts significantly faster than in this previously calculated example. So for that we need to change 2 parameters in this fly ash param entry. For this 5PL equation, we change the parameter b to 0.6 and write in a comment that it was 0.7 so that we could get it back if necessary. And we change the parameter d to 120, which is twice as much as it used to be before. So now I have recorded what it was and what I have now set. Of course, in reality, these parameters are normally fitted from quantitative X-ray analysis data, but we are just doing quick test. So now, after this is changed, we can rerun the process and see what comes out. So we click on simulate and watch. So now the simulation is completed, and we see that indeed now the curve for fly ash goes pretty much higher, and especially in the second half of the plot here in this area. And when we change to watch volumes of phases, we can also switch to stacked areas. This is more convenient. We can see that the pattern has changed indeed. First, what we see is that the fly ash is dissolving significantly faster. Accordingly, more siliceous hydrogarnet is forming. Also somewhat more CSH, however less portlandite, because fly ash is not so rich in calcium. And then at some point on the right side of the diagram, we start forming stratlingite, which is more silica-rich phase, at cost of monocarbonate. So we can see now how this change in hydration kinetics can affect. This is calcite, which is more or less containing part of extra calcium as well. So this illustrates how to handle the Params entries in process settings table. And I wish you with this good luck in using the upgraded CemGEMS, and hope it will be helpful and useful, and let's see what new comes out in the next release in 4 to 6 months. We will mainly concentrate on graphics. Goodbye, everyone. Ciao.